Welcome to the fourth and final video for this section. Hopefully this is shorter than the other ones, but we are going to look at some more applications. Now before I get started, I do need to give you the video quiz passcode. So the passcode for the video quiz 3.5 and 3.6 is, capital E, lowercase x, lowercase p, capital G, capital R, capital G, lowercase r, lowercase o, lowercase w, th, exponential growth, just abbreviated. So capital E, XP, capital G, ROWTH. Okay? So there you go. You can use that to access the quiz. Alrighty, now onto the applications. I have to clean up a few things that I kind of glossed over. So I would be remiss to not point this out. Any exponential function of the form p sub 0 b to the t can be expressed as this. What you can do is say that, well, this b, we're going to have to insert an identity. We would just say that b to the t, that we can say this is the same as e to the natural log of b all to the t, and after you use properties of exponents they end up changing out. So then really when we look at k, k can be really expressed as natural log of b if we have equivalence between these two models. Okay. Now the other thing is that when we use exponential growth models, we assume that there are plentiful resources. So for example, right now in the world, COVID-19 is spreading rapidly, at least in the United States. And so in that, right now, we can assume that there are plentiful resources, plenty number of people, that is, for the coronavirus to go through. So that's why we can use exponential growth model in certain cases. Now, if this is not the case, what do we use? And that's where the logistic model is another model for growth that can incorporate some more real-world restrictions, one of which is kind of limited resources. So this curve is very, very interesting, the curve that this function makes. So we'll take a look at it in this next example. But as an example, California's population can be modeled like this, using t as the number of years since 2000. So we just want to first graph it and then describe it in words, and then we want to determine the population in the year 2000 and blah blah blah. We'll get through it. So we're just going to use this in Desmos. So let's hop over to Desmos. So I went over to Desmos and graphed it, and here's what it looks like. And so I zoomed out a little bit. If you wanted to like flatten this out or compress it, you could. But this is what the graph looks like approximately. Okay, so a little bit different than exponential, right? If we look at it, it looks kind of more almost like a cubic function, or like a cube root rather. So it grows slowly and then it sort of plateaus, right? It asymptotes. Ooh, fancy vocab. But so that's what it looks like. Okay, so now what we would say is it grows kind of steadily until a certain time, and then it levels off. That might be our description for part A. Write it down if you wish. I'm going to move on. Part B, we want to find the population in the year 2000. Okay, so that is to say, t is the number of years since 2000. So that's, if I want to find the population in the year 2000, that's the same as saying find p of 0. Oops, not 10. P of 0. And so then this is going to be 95.2 over 1 plus 1.8 e to the 0, right? And then so this is really the same as saying 95.2 over 2.8. And if we type that into our calculator, we get 34. So 34 million. That's nice. Okay, so that's part B. Okay, and I'd write a nice sentence to that effect. on my own time. Okay, part C, determine the time required. Okay, so time required, I need to know T, for the population to double from that of the year 2000. So I want to know when P is now 68. So I would set up the equation. 68 is equal to 95.2 over 1 plus 1.8 e to the negative 0.018t. Okay, now how in the world do we solve this? Simple. Cross multiply. And include a 1 in the denominator. Cross multiply. I get 95.2 is equal to, and then 68 would distribute to both of those. So 68 plus 68 times 1.8, whatever that ends up being. So 68 times 1.8, 122.4 e to the negative 0.018t, and then now I subtract 68, and 27.2 is equal to 122.4 e to the negative 0.018t. Oh, and this is an equation I know how to solve. Divide 122.4 log, okay, and I'll let you fill in the work. At the end of the day, what I get is t is equal to the natural log of 27.2 over 122.4 divided by negative 0.018, which is approximately 83.5. So I would say sometime in the year 2084. Okay, so it would occur after year 2083, sometime during 2084. Okay, what is the limiting value under this model? Well, that is where that graph would be handy. Okay, but I will tell you that it ends up being 95.2. Okay, notice anything about that and where I got that from the equation? But anyway, this example is just meant to give you an alternative function or an alternative model to the exponential growth and decay model that accounts for limited resources in an environment and where we're looking at the population. So exponential growth, great model for an assumption where we have plentiful resources. I don't want to say infinite, but plentiful. When we have limited resources, this is where the logistic model comes into play. Okay, so again, make sure to go back and complete the video quiz now, and we'll see you in class to discuss all this further.